The last concern in the lesson is estimates. Suppose that we have a series 1 over n cubed, and we expand it out. Suppose we write out a few terms here. 1 over 1 cubed, 1 over 2 cubed, 1 over 3 cubed, and let's say that we stop at the 10th term, 1 over 10 cubed. And rather than going out to infinity, we are just taking 10 of them as an approximation of the sum. The question would be, how accurate is that? If we do the arithmetic, we get 1.1975. Please do not round. The remainder estimate is that the rest of the terms, the 11th on, has to be smaller than this integral, 1 over x cubed, from 10 to infinity. If we carry out the integral, we get 1 over 2n squared. If we do the n, the improper from n to infinity for 1 over x cubed, it's true that we would replace that with t. Take the limit as t goes toward infinity. It would be a power rule, and we get x to the negative 3 becomes x to the negative 2 divided by negative 2. The limit as t goes toward infinity on negative 1 over 2x squared from n up to t. We can do the substitutions, and when we do so, the limit as t heads toward infinity, 1 over 2 to the 2t squared minus 1 over 2 to the 2n squared rather. This ends up heading toward 1 over 2n squared. And if we make the substitution back up here, it's true that that would then come out to be 1 over 2 times 10 squared. So if we carry out the improper integral and get a value for that with n, leaving n as the lower limit, still doing the limit as t goes to infinity, we'll have a formula. And if we stop at 10 terms, we can substitute 10 in for n, and we have an approximation for the area, which is this idea of 1 over 200 being the error. So this answer is within 1/200th of the complete sum. The last piece of this is, suppose that an accuracy level is set. Suppose that for this particular series, we wanted to be accurate to within 0.0005. Again, the remainder estimate comes from the improper integral. We won't rewrite the whole thing, but the formula for that was 1 over 2n squared, or 1 over 2n squared. You will have to carry out that improper integral to begin with. After we have a accuracy level set, it is simply a matter of saying that the error, 1 over 2n squared, has to be smaller than the accuracy level set. Carrying out the algebra, we can multiply by n squared and divide by 0.005, and n squared turns out to be bigger than 1 over 0.001, which is 1,000. So n has to be bigger than the square root of 1,000, and that's around 31.6. Since we are talking about integers, we would want 32 terms. Once again, we would carry out the improper integral with n as the lower value and infinity as the upper value, get a formula for it, set that less than the accuracy level, carry out the algebra to solve for n, of course round up because n has to be an integer. So if we take 32 terms, we will have a sum that is within 0.0005 of the infinite sum.